My poster is titled Correlated Computations of Magnetic Anapole Susceptibilities of Molecules and Their Classification on the Basis of Response to Generally Non-Uniform Magnetic Fields. So we want to compute magnetic anapole susceptibilities, the electronic anapole susceptibilities, and we want to study the performance of correlated methods in this computation, and we also want to classify these molecules as paramagnetic and diamagnetic depending on their response to non-uniform magnetic fields. Now, first and foremost, we have the Hamiltonian, where the magnetic field appears explicitly in the spin-Zeeman term and in the kinetic energy term. The magnetic field is expanded as a linearly changing one, and the gradients are collected in this small matrix B. The curl of the total field is called C, and it is related to the antisymmetric part of B. Because we want to do finite field calculations, it is important to have gauge invariance, and we use London orbitals for this, which makes our MO coefficients and integrals complex valued. Now, what are anapoles in general? They are moments which couple to the curl of the magnetic field C, and classically they arise from the meridional currents in a toroidal charge distribution. Very simply, the anapole susceptibilities can be defined as second derivatives with respect of the energy analogous to the magnetizability. So the magnetizability is with respect to B, and there are two types of anapole susceptibility: A, which is second derivative with respect to C, and the mixed anapole susceptibility, which is with respect to B and C. Now, the normal classification for dia and paramagnetic comes from the trace of the chi matrix, and this has a problem for some molecules. For example, for BH and C4H4, not all the diagonal values have the same sign. 2 are negative and 1 is positive, and the trace turns out to be positive for BH and negative for C4H4. However, the behavior of the two molecules in a magnetic field are very, very similar. A positive value means paramagnetic. So BH is called paramagnetic, C4H4 is called diamagnetic. Also, the problems that correlated theories or theories in general face in computing magnetic properties of these molecules is also similar. So we feel that a more fine-grained classification which takes into account directionality is important. Also, why not non-uniform fields? Why do we need to classify only with respect to uniform fields? So to do this, we propose a matrix zeta, which contains all these quantities, and we diagonalize it. And if even one eigenvalue is positive, we call the molecule paramagnetic. So the usual candidates, which are known to be paramagnetic with respect to uniform fields, all show up with at least one positive eigenvalue over here. However, there is a surprise entry. There is HOF here, which is the brick red dot. Now, why does this show a positive eigenvalue? This is because it shows paramagnetic behavior with respect to C, while it is diamagnetic with respect to B. So this is an interesting situation, and we study this further and see that the two behaviors of BH with respect to B and HOF with respect to C is truly similar. They show a paramagnetic effect and then a quadratic Zeeman effect. Okay, now these two challenging cases are very difficult for correlated theories. And so I have only shown the error plots for different DFT functionals and MP2 over here. Okay, and as we know that for chi, as in the plots below, the diamagnetic molecules are much easier to predict than paramagnetic. So it is for the anapole susceptibilities. We have also studied the spin effects, but you can read about this in my poster. And the other interesting point is that the trace of the mixed anapole susceptibility tensor is related to the chirality, and we can show this for H2O2. Thank you for this opportunity. I will conclude here.